Okay, good morning, everyone. So we're going to start the class. So I asked you yesterday to go over example 12, right? So how to maximize a utility function. So first of all, right, the main trick, in our class is going to be to play with utility functions. That's half the trick, right? The other half is going to be to play with proofs and to play with orders, right? As we studied yesterday. But let's go now with something simpler, so closer to undergrad and your previous background. So usually we model consumers as maximizing a utility function, right? In this world, what is the choice set? Is going to be x is equal to R2, right? And then in this particular case, we're also going to assume that this consumption set is going to be positive, okay? So when we're going to maximize this, notice that when we're choosing x, there is also positivity constraints, right? And so they can be 0 or positive, and they also have a budget constraint. The budget constraint can be written as a less than equal or with equality. In the most general case we will study will be with a less than or equal to income. I'm gonna be more formal about the whole notation, but right now it's very understandable that if you have a bundle, which is a vector in R2, and I apply a utility, my utility in this particular example is a linear utility. The linear utility is what's called perfect substitutes, right? Why? Because you have each entry added up. So basically, this is representing preferences such that the consumer basically is going to pick more of any of the two goods, and they basically are considered as perfectly substitutable. So I can move away from one to the other. I don't really care for one in particular, right? And then, I have my budget, where the budget is basically the classical budget that we're going to study a lot in this class, which is the linear budget. It's not the only choice set situation, right? You can have different choice sets, and part of our theory is going to generalize to most general budgets. But the classical one is the linear budget. And the linear budget basically is composed by a price. So, and again, a vector in R2, which is strictly positive, P1 times X1 plus P2 times X2 equal to an income. Income or wealth, Mascolel calls it the wealth of the individual, right? Income has a different, sometimes connotation because of macro, right? So we use the W, so wealth, right? And you can read in Mascolel what we're thinking about when using about wealth. Right now is a very simple model. Wealth in general is a more deep concept, especially with credit cards and other real life aspects. But right now you can imagine a simple consumer problem in all times, right? Where you have an amount of money in your pockets and you want to spend it, right, in two particular quantities. The quantities here are fully divisible, so you can buy basically in the whole plane any particular fraction. So here you can buy 1.0001 of a good. So here you can imagine that we're low in fractional trading, right? Buying a portfolio of these two things, right? And basically we can buy anything we want in the plane, so with any decimal precision. So of course, that's an abstraction. In real life, usually it doesn't work like that, except in very, very specific setups. And of course, if you go to the supermarket, you usually cannot buy 1.0001 kilograms of anything, right? So you have sometimes to buy discrete quantities. So this is basically an abstraction, right? And a little bit what all of this is done in the background to be able to have something where we can apply tools from calculus and optimization, right? So one thing I want you to realize, when in the previous class we described the maximal element of a given ranking that represents preferences in a set which represents a choice set, was that you basically define logically that any item that is not dominated strictly in the preference relation, right, correspond to the maximum. That sounds very nice, is logically consistent, but when you want to do it in real life, it's very hard to do. So no computer is actually able to do that in an easy way. In fact, that problem is what is called NP problem, right? So potentially it's very complex to solve, and no computer can solve it, okay, sometimes. Okay, not all problems, but some of them are super hard to do. So in particular, this is an instance of that maximization problem we saw in the previous class, in the very last part. But this is a tractable model, right? We are able to solve it completely. And that's why people use this, because it's more tractable. Okay, so all in all, I asked you to solve it by yourselves. And what was the difference from what you saw in undergrad? So in undergrad, usually the technique is to take the marginal rate of substitution, right? So derive the utility with respect to x1, derive the utility with respect to x2, put them in a ratio, in a fraction, and then equate this to the ratio prices, P1 divided by P2, right? And from that, which is the marginal rate of substitution, you start solving for x1 and replace it in the budget constraint to obtain x2, right? And then go back to the original expression to get x1. So that's a typical way to solve many models. In particular, these are assuming that solutions are interior. So what does it mean when you have an interior solution? It means that quantities are usually strictly positive, and they satisfy the first order conditions of an optimization problem with equality, okay? Now, that doesn't have to be the case. So in particular, in this model of the perfect substitutes, there is no interior solution, right, in general. So we have to solve it using these techniques of the Karush-Kuhn-Tucker. So the KKT are basically Karush-Kuhn-Tucker conditions, and they will basically tell you the following. So start with a Lagrangian, right? You write down the utility here plus a multiplier, the Lagrange multiplier, parentheses the constraint, W minus P1 x1 minus P2 x2. And note that when maximizing this object, we're going to maximize with respect to x1, x2, and the Lagrangian. Okay, we're also looking for lambda. Usually, you know, you're finding here, you're dealing with a particular utility, which is in fact concave. It's even more than concave, it's linear, right? So first order conditions are not going to be only necessary for finding an optimum, but also sufficient, okay? Now we're gonna look at the first order conditions. So the first order conditions, as I asked you to describe here, to read yesterday, are a combination of what is called complementary slackness conditions. So first, there is something similar to the marginal rate of substitution, but instead of an equality, you have here an inequality. So let's follow the recipe. What this is saying is basically the change on the utility with respect to x1 minus the Lagrangian multiplied by the corresponding price is less than or equal than 0. So let's go to the Lagrangian, right? And basically this is telling me, right, that this is an optimality condition, allowing for cases where, because of the positivity constraints, right, you cannot really hit with equality the first order conditions. So you have an unconstrained optimum, right? You can just maximize this objective by finding the first order conditions. So there is going to be a critical point whenever the derivatives, right, are equal in this case to the price. And imagine there is no budget, so just the derivative is going to be equal to 0. So that's a critical point, right? You learned that in calculus, very simple. Now here in the work with constraints and with non-negativity constraints, you have to be careful because sometimes there is no critical point in the usual sense, right? There is only this, instead of holding this with equality, which would be a critical point, instead it only holds with inequality. So in particular, we're gonna have two cases. The case with equality is an interior point. So this is the traditional way to solve it. This will map exactly to this formula here. So the case with equality, okay? And the case with a strict inequality, which corresponds to this corner solution case. Okay, so right now we're gonna write the two conditions at the same time, so with less than equal symbol. So 1 minus lambda P1. Why 1? Because x1 derived is a linear function, so it's just 1. And then the formula tells you minus lambda multiplied by P1 less than or equal than 0. And here comes the important part. So in the Karush-Kuhn-Tucker condition, you know, they tell us this very nice complementary slackness condition where basically you can do kind of a electric switch. So this can be on or off. So if it is on, then the first order conditions hold with equality. If it's off, then the first order conditions may not hold with equality, and hence it has to be that the XL of the corresponding good, in this case x1, has to be a 0 So it's actually on the corner. So it's a corner solution, okay? So look at this, x1 multiplied by 1 minus lambda p1. So what is inside the brackets is, again, the first order condition, right? Now, because this is multiplied and this has to be equal to 0, so logically it tells me that either x1 is 0 or the brackets are 0. Agree? So in other words, if the brackets are 0, then everything holds with equality, right? So this also holds with equality, and this x can be positive, Do you understand? So basically, if the brackets hold with 0, then the x1 is allowed to be positive, okay? So that's usually compatible with interior solutions. Imagine now that this inequality here holds with a strict inequality, okay? So this part will never be 0, right? So it must be that x1 is 0, okay? That's how it works, okay? So if the first order conditions do not hold with equality, then the x1 has to be 0. That's the complementarity condition, okay? So right now we're gonna see what happens, right? So I write the same thing for the second root. So 1 minus lambda p2 is exactly symmetrical, less than or equal than 0, x2 brackets 1 minus lambda p2. And then finally I write down the budget, okay? So whatever solution, so what is a set of solutions? I have to find an x1, an x2, and a lambda that all of these three inequalities and equalities have to hold. So all of this is a system of inequalities with three unknowns, x1, x2, and lambda. Do you understand? So the Lagrangian will, through first order conditions and Karush-Tucker conditions, will be transformed into, optimizing the Lagrangian will be transformed into a system of linear, now linear, but in general might be non-linear, linear inequalities. In fact, this is non-linear, by the way, it's quadratic because there's x2 lambda. So in general, a non-linear system of inequalities on three unknowns, x1, x2, and lambda. Agree? Okay, simple, right? Now we go and try to solve this. And the way that we solve it is by cases, right? So first, imagine that x1 is 0, right? So this part is 0. So hence, the brackets can be less than, strictly less than 0. So first of all, because of the budget, if this is 0, right, I get immediately a solution for x2, right? So x2 just from the budget has to be equal to, x2 is equal to w divided by p2. So by simple logic, if you don't buy anything of good one, then all your budget, because it holds with equality, will go to good 2. Agree? Right? So, but now if that's the solution, then I replace it in these conditions here, right? So, and then what I realize fundamentally is that for x equal to 0, it can be that this condition holds with a strict inequality, but the other, which is interior, right, has to hold with equality, okay? So let's try this case. And now out of this analysis, I can just conclude by combining them both and knowing that lambda can be thought as a positive Lagrangian, even without knowing the actual value. So I just divide the two inequalities and I get the following inequality that is implied by this combination of the two first order conditions. And this is telling me that P1 divided by P2 is greater than or equal than 1, which is equivalent to saying that P2 less than or equal than P1. So now, these mathematics are telling me that whenever the price of 2 is less than or equal than the price of 1, I end up buying everything of good 2 and nothing of good 1. So let's do a sanity check. I told you that these utilities are perfect substitutes, right? You agree with me, right? So now imagine without math that this brain represented by a perfect substitutes kind of utility is offered a price of good 2 lower than the price of 1. What would this person, this decision maker that is considering good 1 and good 2 as perfect substitutes, going to do optimally? So they're going to buy everything of the good that is the cheapest, right? Do you agree? So that's exactly what this is telling me, right? So it makes sense. Notice that in this particular case, I didn't need to solve for lambda because I already obtained the values of the quantities I care, right? As a microeconomics guys, I want to get the quantities of x1, x2 that satisfy the budget, and that's it, right? Those are the demands. So sometimes, you don't need to solve for the lambda, okay? So in many cases, if you get away with not solving for the lambda, you're great, right? So you're golden. Sometimes you need to solve for it, right? As a requirement to get x1 and x2. But in this case, I don't. And I just characterize the first case. So the first case basically tells me that I guess and verify. That's the technique solution here, right? So I guess the solution basically, and I check that all the conditions are verified. So this proposed solution, x1, x2, is in fact satisfying the Courage-Tucker condition, which in this case are necessary and sufficient for optimality. Okay, do you understand? So this is basically the first part. Now, let's do case 2. So case 2, imagine now that P1 and P2 are exactly equal, right? If that's the case, then it turns out that x1 can be actually anything. So how do I know it? Basically, I can take with P1 equal to P2, I can take any x1 in the interval 0 divided by 0 to the W divided by P1, and I can verify basically there is all of these are solutions. So I can just go here and start verifying that all of these holds with holds in the Courage-Tucker condition. So this is something you can do, very easy to do. And in fact, here there is a claim that is related to a theorem I did in the notes, which is saying that you have a unique solution whenever your utility is strictly concave. So in this case, right, concavity, you can go to the definitions of this mathematical object, right? In this 2D example, right, concavity will mean that you are kind of describing kind of a mountain kind of shape. And hence, if you have this strict concavity, then you're going to find a unique maximum. In particular, when you're flat, like in this case, so this is a linear utility function, you may have more than one solution. And here you can see that, in fact, there is a continuum of solutions. So anything in the interval 0 to income divided by P1 is a solution. So now, again, let's do the sanity check. You are a perfect substitute decision maker. You're offered the same price of P1 and P2. So what happens to your choice? It becomes you're fully indifferent, right, among any quantities of x1 and x2. So what quantities of x1 and x2 can you buy? All that are feasible. What quantities are feasible of x1? From 0 to the maximum quantity, which is W divided by P1. You cannot buy more than W divided by P1 because it's above your budget. But otherwise, you can buy any combination, right? Because prices are equal, perfect substitutes, you're fine. This is the logic, but the math basically requires you to check that when the two prices are the same, then basically all solutions, everything is allowed. So you can verify that all of x1 from 0 to W divided by P1 hold. Now, final case is the mirror image of the first case. So you can just play with the second proposal, which is x2 is 0 and x1 is W divided by P1. And then you just verify it's also solution. And now you're going to find that this happens whenever the price of 1 is less than equal than the price of 2. So as you can see, maximizing a utility function is actually in many cases non-trivial, especially when there are corner solutions, right? This is a very simple case where our intuition can help us, right? Because we know kind of what is the solution of this kind of decision maker just by using words and common sense. And then, we use the Courage-Tucker to verify that these guesses are right. Is there a kind of a map or formula or recipe to solve these things? Not really, it's a lot of practice. And in fact, a lot of this maximization is going to be done by really playing with different utilities, and that's it. Now, so who among you has maximized the famous Cobb-Douglas? Let's do another example, and with that, we're going to.
Professor, could I ask you a question about the solution of this problem?
Yes, go ahead.
So when you state the cases, the different cases, especially when you assume that the quantity demanded of one of the two goods is equal to 0, does it necessarily follow that the first order condition of the other good holds with equality?
No, it doesn't, right?
Okay.
So basically, remember, the only requirement here is less than equal, right? Less than or equal to. So as long as these conditions hold, there is no need for the other to hold with interiority, right? In this case, right? So if you go and try to verify it, right? There can be even multiple solutions, right? Some lambdas for which it doesn't hold. So that doesn't really concern me, right? As long as this solution satisfy the conditions, is fine, right? So we're just guessing and verifying. So that's the technique I'm using here. So I don't need it to have a particular, so there is no requirement. That's the short answer. There is no requirement for this to be strictly less or equal to. It has to be, can be either of the two, if that's what you're asking.
Yeah, but in that case, could I, for example, assume that case 1, but with the second first order condition holding with inequality, and see what happens there? Or it doesn't make sense?
Remember that the exercise is you propose one solution, right? And you're trying to see if there is if this solution satisfies these conditions. So I don't know what you are gaining by checking whether this holds with strict inequality or equality. There is no information there. If you find one, you're fine.
Okay, but how do I know whether there are more solutions than this one?
That's a different question. So okay. How can you know if there are more solutions? So this is a problem. This is a question in general for optimization. So when you don't have a unique solution, so when you don't have a guaranteed unique solution, then there is always this question, right? So in particular, you can take these things, right? And in particular, we know that for the case of linear functions, which are concave, right? These are necessary and sufficient. So it means if I find all solutions to this system, then I'm done, right? So in this case, just for the sake of the example, I'm simplifying. I know already which are the set of solutions, and I'm verifying them in the Karish-Tucker conditions. That's the example exercise. Now, as you well mentioned, Martin, in the special case of concave utilities that can be linear, right? So weakly concave, if you want. You don't usually say weakly concave, you just say concave. You can use the Karish-Tucker conditions as necessary and sufficient, which means that finding all solutions to the system of equations is enough. Now, that sounds easier than what it is, because finding the whole set of solutions of a nonlinear system of equations is the same nature of the problem of optimizing and finding all solutions when you have multiple solutions. So you don't really know. Like, for instance, imagine I put this in MATLAB in Julia, right? And then my prices are the same. P1 is equal to P2. If I'm maximizing this in a computer, the computer is going to find one point here, right? Between 0 and WP1. And that's one solution, right? Do I know if there are other solutions? Well, one way to do it is to change the initial conditions. So any numerical optimization algorithm will start from some initial guess, right? So you can randomly change the guess, right? And then let it converge. So possibly you will converge to a different point. In reality, because there is a continuum of solutions, can you really find them all? Not really, right? So that's my main point. So what you're asking is a practical question. So in reality, when you have multiple solutions, it's not easy to be sure, especially with very complex utilities, that you are finding all solutions. So the mathematical guarantee would be to find all solutions to the implied system of equations of the Karish-Tucker conditions, because they are necessary and sufficient for the case of concave utilities. So if you have the guarantee of concavity, you can start looking for all of them, okay? But in general, this is a complex problem. So that's why, in many cases, modelers try to change their models such that you actually imply a strict convexity, or what it means for utilities, a strict concavity. So in that way, there is a unique solution, right? And if you find one and you verify it's a solution, then it's the only one because you have a theoretical warranty, okay? So multiple solutions are always an issue in practice and in theory, because you are always unsure if you find them all, even if it's easier said than done. So the theoretical warranty is if you find all the solutions to the system of equations and you are concave, you're done. But again, it's not easy to do, especially in complex models, okay?
In the case that the objective function is not strictly concave, is it sufficient or useful at least
it's not
plot the objective function and the constraints and see what the candidates for the solution are, or it is not?
Imagine the utility has some weird term, right, that makes it not concave. If that's the case, right, the Karush-Tucker conditions are only are necessary in the sense that a maximum will satisfy them, but are not sufficient. So the fact that you verify the Karush-Tucker conditions doesn't mean you are going to be an optimum. In that case, theoretically, you need to check the second order conditions, right? So basically, you have to derive again and go basically to the Hessian world, and you have to verify you're actually in an optimum, in a maximum instead of a minimum, okay, or a saddle point. So this is basically calculus 3, and you have to study this Hessian and have to study whether this matrix is positive definite, indefinite, or negative definite. So all of this, is kind of techniques for optimization theoretically. In many cases, so there's 2 levels. So in real life, we as modelers have to face usually a lot of non-convexities, right? So what people do, you can try to check second-order conditions and so on, but right now the state of the art is basically that maximizing not concave objectives is usually an art. So the way you do it is with a lot of different starting points, different algorithms, trying to explore the big parameter space. But this is an open problem. So if I'm going to be direct with you, nobody knows really how to solve non-convex problems. This is very hard and is an art. However, you cannot avoid them usually. So non-convexities arise because of many reasons, in particular when models get more complex. For convex models, there are a lot of algorithms that guarantee describing the set of solutions, right? Mainly because even if you have some properties of the maximizer that we're going to learn in a bit, so I'm not going to run ahead of me. But one property that arises is that the set of solution is convex. For instance, say here is a unique point, so that makes it convex trivially. But this is a case where you can see convexity. So this is basically ruling out cases that you have 0 and you have WP1 as a solutions, but nothing in between. So convexity will require that basically, if you find the extreme solutions, right? So the minimal solution and the maximum solution, then you can find all solutions because basically you live in a convex interval, right? So that kind of principle allows you to describe set solutions by describing the boundary of a convex body, which is given by polytopes, right? So in other words, convex optimization is easy, and usually you can guarantee describing the set of solutions through the boundary of the convex body. Turns out if you maximize concave utilities, you end up with a convex set of solutions, okay? So you can use that insight to get the description of the thing. In general, if you lose concavity, you don't have that. And then, it's wild west. Very little secret, all of the neural nets that you hear machine learning that people use, in Google, for Uber, and so on, all of them are non-concave. So are very complicated nonlinear objective functions, but they still kind of work, right? So again, so if you are really successful in a particular application, you can actually get very close to to the true solution, even if it's not the global optimum, and still go out with your life. And that's a little bit what, even if mathematically it's not kosher, it's very hard to do, people do it, right? And especially with better computers, more processors, you can explore deeper the parameter space, right? So it's basically right now the current approach is brute force, and you just start searching everywhere, right? And because you have better computers, you're able to get to a better solution. Okay, so but that's basically optimization is an art, and this is just the toy model possible, and there is some structure that we still haven't learned, but mainly what I'm giving you the heads up is that because of concavity, you get additional structure. The set of solutions will be a convex set, and that can be used, okay, to be sure that you're finding everything. And in particular, because it's convex, you can describe the boundaries of the body. In one dimension, you can just describe the minimum and the maximum. But imagine 2 dimensions, you have to describe all the faces of the convex polytope, right? And the same thing you can do in more dimensions. Okay. So that's a great question. Now I'm going to give you another example, and then let's see how you do it. So the utility of X is now going to be equal to the minimum of X1, X2, subject to T1, X1. So you get the deal. So who remembers the name of this kind of utility function?
It's a perfect complements case, right?
Perfect complements, exactly. So please solve it. You have 5 minutes, try it on your own. We have non-negativity constraints, so the quantities have to be non-negative. Okay, so let me put you in a gallery. Then I'm gonna ask you to try to tell me how to do it. Okay, who wants to give it a try? So first of all, we are facing, what is the elephant in the room? So this thing here, if I'm trying to apply the Koreshkun-Tucker, so what is my main barrier to this? This thing is non-differentiable, right? So I cannot derive it. So in principle, so this is something I want basically to understand. So a lot of the problems that appear in the core exam, are going to be like this, solve this in the context of a general equilibrium set. Okay, but if I cannot differentiate, then what do I do? So basically, I try to understand what's up with the model, right? So someone said it's perfect complements. I think it was Ahmad, right? But so can you tell me more? What is intuition? So on how this will. So what will be the solution to this problem just intuitively?
So I was just thinking generally. Here I know we had the opposite extreme perfect substitutes, but there was a lack of concavity, and we talked about what that means. So I'm just thinking that also in this case there would also be a lack of concavity, because we have if I'm just imagining it the way that I saw it in my undergrad or master's, that if you draw it, you will also find that there is only a point solution, and that point will be at a corner, right?
Yeah, but I mean, it's not really a violation of concavity, right? So for instance, let's say I draw the indifference curves of this thing, right? X1, X2, right? And then basically what I'm saying is this is the minimum of X1, X2, right? So basically I draw 45-degree lines, right? And then essentially what I have is these indifference curves, right? So basically all of them map to a different level of utility, right? U2, U3, and this is equal to the mean X1, X2 bar. And basically they are equal exactly. So x1 is equal to x2, right? So these are the famous perfect complements, right? So they are this shape, as you can see in the share screen, right, on the iPad. And then, once I have been able to draw them, right, I also realized the following. So if I try to now see how I will be maximizing this thing. So these are my indifference curves, right? And they're heading this way. And then say I have a budget, right? You see? So then what happens? So where is the maximum happening, right? It's happening exactly at the kink, right? So this is exactly where x1 is equal to x2, right? Okay. And then the thing I have to then do is try to apply this to what I know about the problem. So I know that my solutions are going to happen in x1 is equal to x2, and I have a budget constraint, right? So if I go here, p1 x1 plus p2, and here I replace x2, so x1 is equal to w, right? Which means that x1 is equal to w p1 plus p2, okay? So which means x2 is equal to w p1 plus p2, okay? Do you agree?
Yes, that's very straightforward. Yeah.
Yeah.
I mean, it's.
But now I want you to do something also to realize that still intuition about derivatives kind of works. So let's go back to this part. Okay, so you see the shape. So I'm gonna draw them again. x1, x2, and my indifference curve. Okay. So how can I? What is the notion of the derivative, graphically speaking? So a derivative basically, would be a point where basically there is a tangency, right? So for instance, doesn't this look like a derivative to you? What is the issue with this? Why is not a proper derivative?
The issue is there's no curvature, right?
Yeah, but that means that there is not only one, right? For instance, this does
Yeah.
the same job, right? This one does the same job, right?
Yeah.
Do you agree?
Yes.
So turns out that a collection of all such lines, right? Okay. If I take all of them, I can actually make a set called the super gradient. So in other words, even if the derivative case is a special case where the super gradient set is a singleton, okay? So you have something nice, right, curve, and then I pick a point. Is there any other line that passes through that is still tangent? No, right? So it turns out that, yeah, go ahead.
Because we talked about uniqueness, no, there would be only that one point.
Exactly. So this thing is a unique vector, right? So when it's a singleton, then this is called differentiable. When it's a set, it's super differentiable. Okay. Okay. Yeah. So short story. Any concave utility that has convex indifference curves. As you can see, this is convex because this area here, right, is a convex set, right? So it looks too ugly, so I'm going to delete it. But I'm going to explain a bit convexity again. But basically, anything that looks the same as the usual indifference curves, but has a kink, still has pseudo derivatives, right? And they are basically called super gradients. But instead of being unique, there are many of them, okay? And then let's think about optimality for a second. So in this kind of budget thing, right, basically what you're looking at is a point, right, where you know, the gradient, this vector, which is the orthogonal to the point of tangency, right? It is orthogonal, right, to the budget line. So if I'm trying to maximize this, essentially what I'm looking for is the point of coincidence, right, of this gradient, right, with the hyperplane. And that's the interior solution that we discussed, right? So essentially the fact that the partial derivative of u with respect to x1 is proportional to lambda p1. So that's the analytical description of this geometric fact, right? Do you understand? So, and then, you know, when you have a set, like in the case of the Leontief with multiple lines, right? You change this property to, imagine you have a set here, u, x1. So this is a set. So now you say there exists a vector in the set, right? There exists a vector in the set because this is a set of vectors. Do you understand? Such that the vector, right, is equal to lambda p1. Okay. So let's go back to the Leontief and look at this collection of things, right? There are many of them, but only one of them, you know, coincides. The normal vector of such a line is orthogonal to the budget hyperplane. Do you understand? So here there is a collection of them, right? But only there exists one which is which has the property. So let's go back to the solution. I'm going to repeat it again. You see? So out of all of them, right, there is one. That's the only thing I need. That there exists one in the set that basically is orthogonal to the normal vector. Okay? So in other words, optimization here is the same. So what I'm describing is essentially that even so we switch to not being able to derive analytically using our tricks of derivatives, right? The geometric notion of optimization still is active in the world of perfect complements, right? Even with kings. It's just that instead of having one unique vector that is called the differential, or basically the gradient of the utility, you have a collection of them, right? And then in the new notion of optimization, more general, we just need a vector, right? Out of the set that satisfies the first order conditions. So the short story is essentially that even so, if you are not able to do the classical, just mechanical optimization, you can still use the graphical intuition and the fact that still the optimization forces are at play, right? But in other words, the way to solve this, as I mentioned, is just by recognizing that you can do, you can solve this at the kink, and this is equal to x1, requires that x1 is equal to x2, which implies the solution is this. W divided by P1 plus P2. Okay. So again, so the thing I just mentioned, right, is that the main notion we're going to use through this class is this, Karush-Kuhn-Tucker conditions, but we are not going to necessarily focus our attention on smooth things, right, that have only unique derivatives, but we can have, general derivatives. But in general, the main assumption is going to be fundamentally concavity. Concavity and quasi-concavity are going to be there because they are going to allow us to work mainly with first order conditions. We don't need to check second order conditions, okay? And that's going to simplify our life a lot. Okay, so this is kind of just a refresher on optimization, very bad because the main part of optimization is going to be done in the class with Maria. So in the Math for Economists, right, she does a full chapter on that, on the Karush-Kuhn-Tucker conditions, So I'm happy that she's able to do that. So therefore I can just focus on some particular, tricks and kind of short version for our class. The way it's covered in the math for economy is a little bit more complex. So you end up optimizing these very complex utilities with a lot of constraints. So it's a good training, but in general, this is basically what you need for my class, right? So try to realize that carriage contractors are the main thing to do. And in general, I'm going to be doing concave, so you don't have to focus much on the secondary conditions, right? And these are things you have to practice if you are kind of rusty, but that's it. So the only thing I want you to be aware is that if you were used to, in undergrad, to do the interior solution marginal rate of substitution is equal to ratio prices, that's no longer active here. So very rarely we're going to be there. Most likely you're going to be in this work with corner solutions. And already a preview of the core exam, a lot of the questions in the core exam have to do with these cases that are perfect substitutes, complements, of some weird combination of that, okay? So that's basically what people are going to be playing with, not the classical cases of Cobb-Douglas CES, you see? So basically what you want you to develop basically is that you actually understand the notion of optimization and so on, not only apply the formula of the marginal rate of substitution. So this is a good case example where you realize, how the focus changes, right? Instead of the formula of the marginal rate of substitution, we move to understanding, what is an optimum, okay? So that's basically it. And, the way I presented it, basically is telling you that it depends how your brain works. Some people are really good at geometric intuition, so a good thing to do is to draw it. A lot of the examples and problems, even in the core exam, are going to be 2D, 2 dimensions. So it's possible to draw them, right? And that's going to give you intuition of how to optimize and how to approach. Example being here, perfect complements. You can draw it and see that the optimum is at the kink. This will inform you to write down the equation, right? X1 is equal to X2. So the figure informed me to be able to write the formal proof. Importantly, right, some people are really bad at drawing and they don't have geometric intuition. When I was in grad school, I didn't like drawing. For me, I need to do it fully analytically, right? So I tried to learn more the optimization technique using, this set of derivatives and so on. It's not that hard, and I was able to verify. In the end, you end up mapping this to a system of equations, and then you solve it, right? That's how my brain works. And I was able to, navigate my first year more trying to see it from this mathematical view instead of geometric view. Everyone thinks differently, do whatever is better for you. We're gonna learn more about that, but this is something that's gonna appear as part of a problem. So we're not gonna really focus on making you derive and optimize, but rather, we're gonna learn concepts and then send you to a problem set or an exam, a particular example you have to solve yourself, right? Kind of applying what you know, okay? So this is a good overview. What else I'm going to cover from this part? So the rest of the chapter I asked you to read, as I told you, is kind of a light refresher of things you can see at the undergrad master level. It's more than undergrad usually. I would say is master level micro. So this chapter is kind of a good first overview of the material we're going to cover starting in some minutes. What else I want you to know? I think that's basically it. Yeah, I'm done with that. The only thing I want to also cover here before we go in the chapter 4 is this utility representation theorem to link it to the previous class. Okay. So one key aspect of this class is that we're going to be living in parallel worlds, so to speak. We're going to use the relation language. I got an email from one of you saying, this kind of math is very different from what I have studied in undergrad, right? Because it's ordinal, it's using relation, doesn't use utilities, right? Completely understandable. That's the main thing, you have to learn this class. That's why I started with that. So you have to really read it as a way to understand the new language and mathematical modeling tools, right? So it's a modeling language. So this is something you have to learn, but it's not going to be easy because it's like learning French, as I said yesterday. You need to really get acquainted with the new tools, okay? Now, once you have done that, but also we're going to do in parallel the more traditional way of modeling, which is the utility representation. And the utility representation, as we did in the examples a moment ago, is basically writing down some utility and playing with it. Now, of course, there is a link between the ordinal relations world and the utility world. And that link is called the utility representation theorem. So basically it says that if preferences are complete and transitive, right? And in this refresher, we're just gonna cover quickly the fact that when X is finite, so the choice set is just a finite set of alternatives, then there exists a continuous mapping, aka utility function, mapping from the choice set to the reals such that they represent the preferences. So new word, very loaded. Representing the preferences means exactly this. The utility of A is greater than or equal to utility of B if and only if A is in relation in terms of the preference relation. So it's preferred, or as we say informally, weakly preferred to B for all A and B in the choice. So there is a lot of information here. That's the great thing about mathematical notation, right? Just one liner with a lot of info. So first of all, there is a double arrow. So two ways arrow, if and only if. If and only if means first that if I cut this part of the arrow and I just see the flow from left to right, it means that if the utility of A is greater than the utility of B, then there is a preference relation such that A is better than B. And that preference relation is in fact complete and transitive. Okay? So think about this for a second. What I'm telling you is that if I say my preferences are described, my relation is described by a utility function mapping from X to the reals, right? And the only thing I'm requiring of the utility function is that the utility function is mapping any object in the X to a real in the real line, right? That immediately tells me that the underlying relation is complete and transitive. Do you understand? So that's very subtle. So think for a second about this. So imagine, how many stocks do you think there is in Wall Street? So imagine, the stocks that you can trade in an app like Wealthsimple. How many stocks can you browse, in just the simple app? So it's definitely, a lot of them. I don't need a special number, but it can be 1,000, right? So the choice set there, is basically the number of stocks. That gives you the R to the L being number of stocks. And now, what you're saying is you can take a portfolio, of these things and map it to a single number. So, this is a high dimensional object, is a vector in R, L equal to say 10,000 to say a number. Now you're saying that you're able to map this vector in R 10,000 to one number, the reals. And you can take, in fact, two vectors, right? X and Y, both of size 10,000, and map it to two reals, such that one real is above the other, for instance, right? So you can basically reduce the dimensionality of 10,000s to one. Okay? If you do that, then immediately the preferences describing that behavior is automatically complete and transitive. Do you understand why? So the whole trick of the utility function from the mathematical perspective is that because it maps complex objects in X, right, to the real line, it immediately inherits the properties of the greater than equal relation on the real line. Okay? Do you understand? So in the real line, we have the greater than equal relation, which happens to be complete and transitive, because if I take any two real numbers, I can rank them. I know which one is higher than the other, right? So completeness. And second, because it's a real line, right, I can basically put them in a list, right? So there is a minus and a positive part. I know which number is bigger, and I know if I track three numbers, and first number is below the second number, and the second number is below the third one, it has to be that the first one is below the third one. And also, if I'm talking about the opposite relation above, it also holds. So if I have three numbers, blah, 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 right, transitivity will hold. So do you understand the whole trick of the utility function? So the utility function is taking complex object in X and mapping it to the real line. The moment you're in the real line, you inherit the greater than equal properties, so hence completeness and transitive. Do you understand? So the utility maximization model is a model of reduction of dimensionality. Okay? So basically take huge dimension in X, map it to the scalar line. Do you see?
So just a question. So now if we're using the real line, that means because of the properties of the real line, we don't have to worry about it being transitive or complete because that's already one of the properties and it's one of the nice things. So then we won't have to prove it. We'll just say because we're using the real line. Is that fine?
Yeah, exactly right. That's intuition. So, but you see also here, this is a behavioral model, right? Basically, we're assuming humans are able to be mapped to a single criterion, right? so that's great, and it has been very productive for econ. But sometimes, is doubtful. So we're gonna make a line now and not talk about the model, and we're gonna talk for a second about real life, right? So think about the 10,000, stocks. Is it true that you can reduce it to one-dimensional object? So in some cases, yes, right? You can have, a robot. You write an investor robot, the automatic, robot that automatic trading. And the only thing that the robot does is trying to maximize some sort of yield, right? So trying to get some sort of objective that, in fact, by programming, by construction, is a scalar object, right? So, there can be some things that you can build that look like this, right? So a scalar function. But think of you are a casual investor, you're bored, you have some savings, you want to invest in wealth simple, You go, you start playing. What kind of criterions do you use to rank vectors? So first of all, you have 10,000 of them, right? So somehow it's not clear that you're going to be aware of all the 10,000, right? So you have to have some layer that tells you what to pay attention to. So this is kind of the attention layer. So you're going to have, first some function that's called attention. That's going to map the 10,000 existing assets into something smaller that your brain can handle, right? So that's one layer. Now that doesn't need to be described by a utility function. It can be a more complex object, right? Attention can be modeled in a more complex object. Once you have that smaller object, now how do you rank stocks? Versus how some people buy stocks. So some people say, this stock is good because I consume it, right? I use this thing, so therefore it can be good, right? So for instance, I think that that Amazon is gonna go high up because I use a lot of Amazon, right? So I use it, hence I think it's good. Another person says, I heard from my neighborhood that this stock is going to do well, right? Another person says, I conjecture because of the regulation that this thing is going to happen, right? So you have kind of three criterions going on, right? If you have many criterions about a topic, how do you aggregate them into a decision? So that's an open question, right? So one way you can say, look, I will say this stock is better, this portfolio is better than this other portfolio if among all my criterions possible, right? At least one always says this is better than this. So at least under one of my possible criterions, right? So whether I use it, whether my neighbor that's very smart says it's good, and whether I think due to regulation is going to be fine. So if at least I can justify my choice under one of them, I say X is better than Y. So that's a model, in fact, that is different from utility maximization because it uses three criterions, right? And each criterion can have many layers. So in other words, what I want you to realize is that the utility function is one particular model of behavior out of many, right? That has the gut of telling us that any complexity of the human mind can be reduced to one scalar, one-dimensional object, okay? And that's sometimes super powerful, but sometimes also very reductive, and hence, empirically hard to hold, okay? So that's the model we're going to study, but that's basically rationality for economists, right? And now you can see both the elegance, but also the possible restrictiveness, okay? But, whatever the philosophy and whatever you believe, that's the power of preferences. As Amat said, we know that the moment we marry with a utility function, we're going to get two guaranteed properties, which are completeness and transitivity, right? That's it, okay? That's it. Now, the interesting thing that happens in these two ways arrow is that also the flow from right to left also is true, right? And this flow tells me that, imagine I have a preference on X that happens to be complete and happens to be transitive. Now, this theorem is guaranteeing to me that I can write down a utility function, right, that ranks objects in the same way as my preference function, okay? So it's two ways. So if I start, instead, I just went to Victor's class yesterday, I learned about preference relation, I say, I don't want to use utility anymore. I'm just, black belt microeconomist now, so utilities are too low for me, I don't use them. And then you say, but I still like completeness and transitivity, right? Well, you're fooling yourself because you're still using utility functions, right? This is the theorem. This is what the theorem is telling you. Now, this is true only when X is finite, okay? I'm already telling you this is only true with X is finite because there are some weird cases when X is not finite. Like for instance, in the reals, where you have R2 in the whole Euclidean space. Remember our mostly harmless ordering, the lexicographic ordering of the previous example in the previous class. Remember the lexicographic ordering that basically we had this kind of Maslow necessities, right? So the first entry was more important than the second entry, right? That one doesn't admit a utility function representation, okay? And we're gonna learn why in a bit, but basically this is where the math gets hairy. But and also tells you one important thing. The relations are not only just because microeconomists like math and we like to use new mathematical toys, which is partially true. We do like new mathematical tools for sure. But preference relations are more powerful and more general than utility functions. When the X is finite, basically it's the same, right? As long as you have transitivity and completeness, you can go back and forth. This is this theorem that I'm going to establish in a second. But when X becomes a complex space, like for instance, the space of lotteries, a space of portfolios, right, R2, or even more complex lotteries, right? Think of in macro people have really complex choices. So when you are thinking about macro and your macro refresher, people are choosing over crazy things, right? For instance, you're choosing over lifetime consumption, right? And sometimes lifetime consumption with different states of the world, right? So basically the object of choice is kind of a stochastic process, right? So that's basically your object of choice. So the space of a stochastic processes is very complex. So hence defining a utility function there is tricky. So of course you're able to do it, and macro people are practical guys, so they assume enough until you get back to the utility. But in the highest generality possible, and sometimes you cannot do it, right? For instance, the lexicographic model, coming back to it again, the lexicographic model is a very reasonable model, right? A lot of people think in lexicographic terms. We learned, for instance, during the pandemic, that a lot of policymakers, epidemiology people are in fact lexicographic guys, right? So they want first to, eliminate all cases of COVID, and then, let's think about going back to class, and then let's think about, opening recreation. For economists, for us is a bit crazy because we're thinking more smoothly, right? So trade-offs, guys, trade-offs, right? They say no, lexicographic. So lexicographic, it describes a lot of people, and lexicographic cannot be captured by a utility function. So this means, that in fact preferences relations are more powerful. And that's basically the double message I'm giving. So preference relation are first more powerful in the world of utilities under transitivity and completeness, but become even more flexible when we leave the world of rationality. So if we remove completeness and transitivity, dealing with preference relations sometimes is more tractable, okay? So there is a reason why we do relations, but there is also a bridge to the known world of utilities. And this is going to be established in this theorem. So the first thing, as Matt said, is a necessity. So we want to show the flow from left to right. So if there is a utility function U that maps the complex objects in X to the real line, such that A and B are such that the utility of A is greater than or equal to the utility of B, then the ordering that is defined by this utility, A is preferred to B, is rational because it's complete and transitive, right? So immediately this inherits the greater than equal symbol properties that we discussed. So this is trivial, right? Just one liner. It's not even a formula statement, but it's just inheriting the fact that greater than or equal to is a complete and transitive order in the real line. Do you agree? Right, so the preference relation defined on top of this just inherits the two properties. Done. Now let's do the non-trivial one, right? So, and then I'm gonna, well, I actually did the proof here because someone asked me to do it formally. So I'm gonna do it again. I think there is some value. So if there is a utility function u such that u of a is greater than or equal than b, then I declare the preference relation to be a better than b. I want to check it's complete. So basically I know because of the reals, either a real number is above the other, right? Or the other way, so it's complete. And then transitivity is just the transitivity on the real line. Okay, so it's super trivial, you know, but it's done. Now sufficiency. Sufficiency is the hard one here. So what is sufficiency? Logically is the flow from right to left, right? So I start with a complete and transitive preference relation, and I want to construct a utility function. Agree? That's what I want to do. So let's do it. So imagine there is an ordering on X, so that is rational, complete and transitive. Then I want to show that there exists a utility mapping U such that for any A and B, such that A is preferred to B, then the utility of A is greater than or equal to the utility of B. Okay? So I want to prove that if A is preferred to B for any A and B in a finite set, then there is a U. How do I do it? Well, I'm going to do it by construction. Okay, so this is one proof technique that we use in this class, which is basically constructively create the object that is part of my proof. Because I say there exists a U, right? That's my statement. I can build one, right? So a lot of proofs basically are non-constructive. So they basically claim that there is one such object, and if it doesn't, then there is some sort of contradiction, right? Or you can basically do an existential claim using some techniques in math called the axiom of choice, which is interesting in itself, but I'm not going to talk about that right now. But right now, this is the most direct proof ever, which is I'm going to construct such a utility function. Okay, so I'm going to build one. So, okay. So first, I'm going to define an object that is called the lower contour set. So, microeconomists sometimes are good at naming stuff. Sometimes they are not great at naming stuff. This lower contour set is kind of a weird name, but, we use it. I think a lot of the mathematicians that came into micro when this thing was being developed were French. So, and then therefore you get some of the naming. So the lower contour set, is basically this set that depends on the preference and depends on an item, and is describing all elements in X that are dominated according to the preference relation by X. So you fix X, you fix a preference, and then you take all Y's that are dominated in the preference sense by X. So what does it mean? It means all the objects that are weakly worse than X. Do you agree? Okay. So question, sanity check. So imagine I take the most preferred alternative out of this set, right? So X star, which is the best thing possible. So what is the lower contour set of that?
Is it the whole set?
The whole set. Okay, great. And imagine I take the worst set, right? So the worst thing ever. So it's just a singleton with X itself, right? So X minus worst thing ever, because it's weak preference, right? It will only contain only X, right? By definition. So yeah. So now this is the lower contour set. Now, here's where I use finiteness of the set. I define the utility of any item X as the cardinality. What is the cardinality of a set? I just count the elements there, right? As the cardinality of the lower contour set. Okay? So why did I do that?
Isn't cardinality 2 to the power of the number in the set? Or?
No. So as I say, right? So the lower contour set is just taking all the items that are worse than a given element according to the preference relation, weakly worse. And then the cardinality is just counting the elements of that thing, right? So in particular, right? So imagine I have a finite set with 3 alternatives. I take the best, most preferred alternative, A, right? Say is A better than B better than C. Then under this definition, the cardinality of the lower contour set of the most preferred item will be 3, right? Then go to the second one, second most preferred one, the cardinality will be 2, right? Go to the third most preferred one, cardinality will be 1. So this utility function will map the most preferred one to 3, the medium case to 2, and the third one to 1. Okay, so it will give me a number out of each alternative. Okay, so mapping from the X to the reals. But basically what I'm saying is, you know, I might as well define this in other ways. I did it in this particular way because I'm constructing one utility. The utility does not have to be unique, okay? So in particular, any utility that, for instance, I can add 2 to it, right, will also work. Do you understand? So the construction is not unique. I'm just picking one that is convenient, right? So there is nothing unique about this, but I'm just trying to construct one out of possible others. So I'm gonna go back to the simple case, okay? Now, this is just a proposal. So I propose the utility, but I haven't shown that this is a good proposal. Do you agree? So what is the real check that this is a good proposal? That if I have an element A preferred to an element B, then it has to be that the proposed utility U of A is greater than or equal than U of B, right? That's the final check. So let's do that. So remember this well-definedness that I brought up due to Severin's question last class, and this was saying basically that a function is well-defined whenever it gives you the same numerical value for 2 items in the same equivalent class, right? So here we have an indifference, right? So possibility of indifference. This is a very general theorem. So what I'm going to do is I'm going to take the choice set and I'm going to create something called the quotient set. The quotient set is basically the collection of all the representatives of each equivalence class. So a lot of words, right? But what I'm telling you is something very simple. Is take an indifference curve, right? And shrink it to the representative element. So take any element in the indifference curve, and now I'm gonna say you are the representative of this indifference curve. I'm not gonna deal with the rest of you. I'm just gonna deal with you, right? The unique item, right? So basically I'm shrinking indifference curves to points. So what I'm doing essentially with this operation is I'm removing indifference. So anything that is indifferent among each other will be collapsed like a zip file into an item, okay? Do you understand? Okay, once you do that, mathematically, this is called the quotient set, right? And now I'm gonna define the utility that I constructed right now with the cardinality of the lower contour set on the quotient set, okay? And I'm gonna do it, remember that in the quotient set, the whole trick is that there is no longer indifference, right? Everything is strictly preferred, strictly rank, okay? So I just take 2 representatives, A and B, and I know they are strictly ranked. So without loss of generality, I assume A is better than B, right? On the quotient set, which is just inheriting the strict part of the original preference relation. And I realized basically that this holds whenever A is strictly preferred to B. So basically I'm taking elements of one indifference curve that is lower and another representative element of a higher indifference curve. And I know that the element on the highest one is above the other representative element, right? Do you agree? It's a simple construction, right? So once you do that, I know for sure that when I define this cardinality of the lower contour set of X in this world, I am sure that X is different from Y. I just have to show, right, that whenever I have 2 elements in the same equivalence class, then the lower contour set of both are equal, right? In fact, we know by definition that the lower contour set is exactly the strict part, elements that are strictly dominated, union the indifference curve associated with X, right? So essentially, you know, we know now that these two elements for any X and Y, such as X and Y, are indifferent to each other, right? We're going to use our properties, right? So first, imagine set belongs to the equivalence class or the indifference curve associated with X, and according to this preference, then it must be that set is indifferent to X. By assumption, X is indifferent to Y, right? By transitivity, what do I conclude? That set is indifferent to Y, right? So remember, this part here is an assumption. This part here is the definition of the indifference curve. Now I take set and I take Y, and then due to transitivity, I conclude that set is indifferent to Y. Now this means that set also belongs to the indifference curve associated with Y. Now I have to do the other way, right? So start set in the indifference class of Y. That means set prime is indifferent to Y. By assumption, Y and X are indifferent to each other. Of course, I'm using here symmetry for the indifference part. By transitivity, I conclude that set prime is indifferent to X. Hence, it means that set prime is in the I set of X, which means that the two sets are the same. Okay. So you see here, so I just unpacked the definition. So you intuitively know it's true, but we're breaking it into pieces, right? And formally proving them, right? Using transitivity of the indifference part. Do you understand? So a lot of the difficulty of this proof is trying to remove your intuition, right? And breaking it into formal steps, okay? That's the only thing we're doing. So you know if two elements are, so when I say you know, I mean intuitively you know that the indifference class of X and the indifference class of Y, under the assumption that X and Y are indifferent, have to be the same set. You know it, right? When I say know, quote unquote, is intuitive knowledge, right? But we haven't proved it, right? So now I'm going to prove it, and this is the formal proof, right? How do you prove two sets are equivalent? The formal way to do it is take an element in the first set and show that if this element belongs to the first set, it implies that it belongs to the second, right? And then you do the same in the other direction. Take the second set, take an element in the second set, set prime, and show that set prime belongs to the first set, right? Which is exactly what I did. So that means that double inclusion, right? The first set is weakly included in the second, and the second set is weakly included in the first. Putting them together, it means that the first set is equivalent to the second set. Do you agree? That's what I did, right? Okay. So now basically what I show is that whenever you have two things that are indifferent, the utility function created using that thing is going to be the same, right? By construction. So now the final thing I have to show is that if I have A preferred to B, it has to be that this cardinality of the lower contour set of A is greater than or equal to the cardinality of lower contour set of B. I'm going to use again my properties. So if I say that the cardinality of the lower contour set of A is greater than or equal to the cardinality of the lower contour set of B, this is equivalent to saying that in the sense of set inclusion, the lower contour set B is weakly included in the lower contour set A. Do you agree? Right? So
yes,
this is
because all of the elements in B should be in A as well, because they're of a lower utility.
Perfect, right? And the cardinality grows with this thing, right? So it's monotone on this set inclusion. So now take an element, I have to show that then. So take an element C in the lower contour set of the smaller menu. And then I have to show that that element is also on the lower contour set of A. Do you agree? That's the inclusion, right? So now what I do is basically notice that by definition of the lower contour set, B is weakly better than C, okay? Remember that by assumption, what is the assumption here? A is better than B, right? By assumption. So A is better than B. Now by transitivity, what do I conclude? So remember that A better than B and B better than C implies that A better than C, right? Which implies that C belongs also to the lower contour set of A. So this is equivalent to the statement that this thing holds. So we conclude that, in fact, if the preferences are such that A is better than B for any A and B, then there is a map in U such that U A greater than equal than U of B. Okay? So as you can see, I've used in this proof transitivity, okay? Many times, 2 times, in fact. But funny enough, so okay, so done the proof, right? So I proved the flow of the arrow from left to right, right to left. Is demonstrated, right? So QED. Now, a question. Do you notice something weird here? At least curious than weird. I never use completeness in the sufficiency part. Do you know? Do you see it? Basically, in any step in the sufficiency part, I use completeness. So I just started with a relation, right? And then I define a utility. And then basically I show that whenever A better than B, then this constructed utility U of A is greater than or equal than U of B. And to show that, I use transitivity. Okay? That's what I did. But I never use completeness. Okay? So if I never use completeness, formally what I show is that if I take any relation, possibly not complete, right? There exists at least one utility that represents the incomplete yet transitive preference relation. Okay? Didn't I? I actually formally did, right? So take any relation, remove now completeness, throw it out, right? So now there exists at least one utility that represents such a preference relation, not such that A better than B implies one side of the arrow than the utility of A than the utility of A is greater than or equal to the utility of B for some utility. Now, but completeness is part of the theorem, right? So when I remove completeness, the part of the theorem that is going to be false is that when you have A better than B, then, you know, the utility of A is greater than or equal to the utility of B, okay? So when you have A better than B, you can remove completeness and there exists a utility that does the job, right? But basically, the moment you have a utility, right, you are implying completeness. So remember that this is just inheriting from the real line. So the double arrow holds under both completeness and transitivity, okay? But one part of the flow, in particular from preference to utility, holds only under transitivity. So the broader lesson here is the following, right? So completeness, as you can see, is basically the property that allows me to close the circle, right? So creates the bridge completely, right? If you remove completeness, you are going to lose basically the uniqueness of the representation. So you are going to get a collection of utility functions that represent the preference relation that is not complete. And moreover, these collection of preferences or criterions basically are telling you that you are no longer a scalar. Do you understand? So for instance, in the example, you can have utilities representing different criterions, like in the example of the asset investment, right? So in fact, I'm gonna write this thing so you have an idea. Boom. This is one example. Sorry. Okay, so show that the following preferences are not complete. Imagine that you have A better than B, even only if utility of A greater than or equal than utility of B for all U in the set Well, let me do it even nicer, so it's more understandable. Okay. So I want you to think about this problem, right? And I want you to work on it. So at this stage, I'm going to stop the basically our recording. And this is going to be where you can actually solve the problem and then basically talk to me next class tomorrow.